हेलो ओके ठीक okay. So we're going to say something related to error. So we know that error is what? Analytical or exact value minus approximate value. The analytical or exact value you will get by standard process of mathematical tools. For example, integration, proper rule you are applying, standard approach you are applying, and then you are getting the output, right? Or you are applying the so different methods to solve differential equation, right? Which is already we have learned through. Through that you will get some answer, right? Y value, and this you are getting by numerical approach, approximate value. So definitely this will share some difference. They will have some difference on the value, right? And so this will have some error. So error are bound to come whenever you are solving something with respect to numerical method. So this approximate value will always come. This approximate value which you are getting from the numerical method only, right? This value you are getting very close to the actual value. So approximate value will come from numerical method. This value you will get from the standard method which you have in the mathematics to solve for a problem. And then you can find the error or relative error. And one of the problem we have seen also where it was asked the percentage error change, right? Now there is a famous error called as truncation error. Truncation error. So many types of errors are there in our mathematics, but this error is very relevant over here, truncation error. So it's an error created by approximating a mathematical procedure. A mathematical procedure, not a number. So many ways you can get error. One error you get in this numerical method is truncation error. So truncation error is an error created by approximating a procedure only, a method only, right? So we have seen that we are approximating a mathematical procedure. Numerical integration, you see trapezoidal method, Simpson's method, right? You see the solution of differential equation, Euler's Runge-Kutta method, right? So we are approximating some in the procedure, right? And due to that we are getting some error, right? We are approximating the procedure in the tan Newton-Raphson also, right? Newton bisection method also, regular false method also. So there we have the procedure in which we are doing some approximation, not and the final answer, right? We can get error in both ways also, right? Suppose you get 2.01, right? 2.01 is the exact value which you get, but you what you took finally, you took two value to work with your forward proceeding. So this error is you're getting due to the approximation in the final value, right? 2.01 was the actual answer, but what you did to reduce our complexity, you have just taken a integer value 2 and then you have proceeded forward for your further working. So this is not truncation error, this is just an error which is coming out due to the approximation in a number, right? But the error which will come here in numerical method, that will be truncation error, because in that whole procedure has been changed, right? We are literally modified. So we are approximating a mathematical procedure over here. So then this completely numerical methods, you get a truncation error, right? So truncation error which we get by approximating a mathematical procedure, not approximating a final answer. So this is not a truncation error, the error which you will get from here, right? So this way the questions are asked, like what is the truncation error in various method. So Euler method we have studied, Euler method, right? Forward or explicit Euler method. So in this Euler method, the truncation error, you have to just remember this, is of order step size square, right? This is order, this is not zero, this is order. These are directly asked, right? Euler method, the error which comes out is of order, it's not a zero, it's O, right? It's of order of S square. S is what? Step size. Similarly, Runge-Kutta second order, if you take RK second order method, right? In that truncation error, is of order, right? It's of order h cube. And RK, Ranjay Kotta's fourth order, the truncation error is of order h raised to power 5. Right, directly these things are asked straight away. Not much detail are asked from here. Just we have, should know that the order is of what size. Similarly, in the trapezoidal rule, numerical integration, right? So in numerical integration, we have a trapezoidal rule. Trapezoidal rule. Right? So here the truncation error is given as, right, minus h cube divided by 12, right? It's a interval, right? Equal interval ni, right? Maximum value of second order derivative at the value c, right? Okay, so this is small n we have denoted, right? The small n. So this is ni, where c, what c lies between a and b, right? C lies between a and b. So a and b are nothing but the upper and lower limit. In that, in between that number, we have c value at which we have to calculate second order value, maximum value of that, and we have to multiply with ni and h cube by 12. Now what is this ni? It is nothing but number of intervals, right? Equal number of intervals. That is given by b minus a divided by h. Now if you put this value over here, so truncation error will come out to be minus h cube divided by 12, and this is b minus a divided by h, right? This is maximum value of second order derivative at c. So h will cancel. So truncation error will come out to be minus h square by 12 b minus a, right? So here we can see the truncation error which is here is of the order h square, is of the order h square. Similarly, we have Simpson rule also. Truncation error for the Simpson rule. Simpson's rule. So for Simpson's rule, this truncation error is given by minus h raised to power 5, 180, right, intervals ni, maximum value of fourth derivative we have to take, fourth. So this is fourth at the at c. So this is nothing but maximum value of fourth derivative of f of x, right, at point c. Now this we know it is b minus a upon h. So if we keep like this, b minus a upon h, so 1 h power will be cancelled, minus h raised to power 4, 180, b minus a, multiply with maximum value of the derivative of fourth derivative of a function at point c. So here truncation error is of order h square, sorry, h raised to power 4. Previous was s square. Okay, so we'll start with the probability. So, so in probability, first we'll have the random experiment. What is random experiment? So random experiment means what? An experiment whose outcome whose outcome is not predictable. Whose outcome is not predictable. Whose outcome is not predictable. That is random experiment. Example, whose outcome will not predictable. For example, tossing of a coin. Tossing of a coin, unbiased coin, right? Or throwing of a dice, right? Etc. So such things, such outcomes we don't know. Whether you toss a coin, head will come or tails will come. We are not sure about that unless and until that experiment is complete. Right. So unless and until that experiment is not completed, we are not aware about what will be the result. So these are the random experiments, right? Throwing of a dice, right? That also random experiments. Similarly, some more terms are there. For example, what is sample space? What is sample space? It is a set of all possible outcome in a random experiment. In a random experiment. It is a set of all possible outcomes in a random experiment. For example, tossing a coin. Example, tossing a coin. If we toss a coin, what are the possibilities? Either it will be head, either it will be a tail. So sample space will contain head or tail, right? Or throwing a dice. Throwing a dice. So what are the possible outcome here that we have to keep? 1 can come, 2 can come, like that 3, 4, 5 and 6 can come. So these are the possible outcomes. If I throw a dice one time, right? One time if I throw a dice, any one of the number can come. Right? Suppose I'm throwing a 2 dice. Throwing of 2 dice. Or, or let's say throwing of 2 coins. Throwing of 2 coins. So what can happen? Suppose I have a 1 coin over here. Right? 1 coin here. Right? When I've thrown this, so I will get head. With that, I can get what? Tail also. Right? If I throw a coin, I can get head and tail. Right? And when you get head in the first coin, the second can show also head and tail. Right? When you're getting tail in the first coin, the second coin can also show head and tail. Right? So you have these possibilities. What you can get by throwing 2 dice? You can head can come, right? Then head tail can come. Or if tail comes, the second coin can show head. If tail comes, second coin show tail. So these are the possible outcomes. So sample space sample space S is equal to head, right? Head tails, right? Tail head and tail. So these are the possible outcome. Then we have an event definition. What is event? Right. So event is nothing but it is a subset of sample space. It is subset of sample space. It is a subset of sample space. Example. Example, for example, if I have a sample space which is containing 1, 2, 3, 4, 5, 6, means throwing of a dice is there, and to which I got sample space, throwing of a dice. Right. So if I create a sample space, or let's say create an event, right? Sample space already, event is nothing but a subset of sample space. So if I create event out of this sample space, so first event 1, let's say it contains 1 and 2 only, right? Let's say event 2, that contains only 2 only. If you take event 3, that contains 1, 2 and 3 only, right? So many events I have created out of the main sample space, right? So many events you can create out of main sample space. So these are the events, right? These are the favorable events, right? These are the favorable events coming out of the main sample space. So events are the subset of sample space, right? So total possible cases are this contained in a sample space. My favorable event to happen is this only, even, right? So event will always come from sample space only. This event 2 need to be favorable, so this event 2 will come out from main sample space. Same goes for 3. If event 3 has to be favorable, right, so this will be coming out of my total sample space, right? And with this we'll connect the probability later, right? Right now we're just looking for the terms. Now 3 most important events are there. Okay. There are 3 most important events. There are 3 most important events. First is equally likely events. Equally likely events. Equally likely events. What is equally likely events? 2 events, A and B. 2 events A and B, right, are called equally likely events. Are called equally likely, right, events if their chances, if their chances of occurrence is same. If their chances of occurrence is same, right? 2 events are there and they have an equal chance of occurrence at the outcome. They are equally likely, as the word says. For example, tossing a fair coin. Tossing a fair coin. Tossing a fair coin. Right? Fair word is also used as unbiased. Unbiased means fair, and unfair, it is used as biased. Right? Tossing a fair coin. Now you see, suppose if I toss a coin, I can get at the max head or tail only, at the max. Which one will come, I don't know. But I can have these only possibilities left over with me. Right? At least sample space tell me that what is the total possible things which will come out in your random experiments. So I can get head or the tail, nothing else. Right? So if you see the probability to come head and probability to come tail, or chances, right now we put chances not probability because probability definition will take later. So chances of coming head is as good as chances of getting tail, because it is a fair coin, right? It's a fair coin. It's not an unfair coin. So here head and tails are equally likely events, right? So head and tails, these are equally likely events. Equally likely events. Likely events. And you know that probability will be half and half. Second type of event is mutually exclusive events. Mutually exclusive events. So exclusive events we want, it means two events A and B, two events, A and B, A and B are called mutually exclusive or called mutually exclusive if nothing is common between them. If A intersection B is null set, right? 5. Right? If nothing is common between those two events, they are mutually separated, mutually exclusive events. And what is third type of event is exhaustive events. Exhaustive events. Exhaustive events. So what is exhaustive events? A number of events event E1, event E2, event E3, event En are called exhaustive events right? If you take the union of E1, E2, right, E3 up to all the events, you get sample space back. This is important. Means all the events, if you take a union of that, you will get the complete sample space from where this all the events has been created. For example, if you see throwing a dice, suppose I take an example, throwing a dice. If a dice is thrown, what are the sample space? That is equal to 1, 2, 3, 4, 5, 6. So let us create an event E1. So event will come from sample space only, right? So let's say event 1 is 1, 3, 5, right? Event E2 will come out of this only, 2, 4, 6. Let's say event E3 is there. That is coming out of this 2, 3, 5. And event 4. And 4 is equal to just 2. So if we talk about event 1 and event 2. So if we talk about event 1 and event 2. So here event 1 and event 2, if you see, if you take a union of that, they are exhaustive event because I get 1, 2, 3, 4, 5, 6, and this is complete my sample space. Right. So even 1 and event 2 are exhaustive events. Exhaustive events because E1 union E2, if you see, you will get 1, 2, 3, 4, 5, 6. And if you see this event 1 and event, let's take event 1 and event 3. So they are not exhaustive because 1, 2, 3, 5, right? 4 is not there, 6 is not there. So event 1 and event 3 are not exhaustive. are not exhaustive events. So because if you do one event union E3 events, you'll get only 1, 3, 5 and 2. So 1, 3, 1, 3, 5, 2. And if you see event 1 and event 2, there's nothing common between them. 1, 3, 5, 2, 4, 6. So basically they are mutually exclusive. Event 1 and event 2 are mutually exclusive. As mutually exclusive, right? And if you see event 2 and event 3, event 2 and event 3, they are not mutually exclusive because 2 is common them. So event E2 and event E3 are not mutually exclusive. Right? Now we see the definition of probability. So probability of any event E, right? Probability of an event E, right? Any event E is there, if that has to happen, right? Then what is the probability of that? So that is given by probability of this event E to happen is equal to number of favorable cases to event E divided by total number of cases. Total number of cases, right? So this is the probability of any event to happen. So or any chances of this event E to happen, that is equal to number of favorable cases to event E. Whatever the favorable cases are there to event E to happen, divided by what is the total possible number of cases which can be possible. Right. Regarding this, we'll see first. So probability of any event will lie from 0 to 1. Right, from 0 to 1. Right. So either the event will happen for sure. So probability will be equal to 1. This is called sure event. Sure event. Event will definitely happen. Right. Or probability of any event can be 0 also. Means that that chances are not there. So it is impossible event. That is impossible event. Impossible event. So either there will be a full chance of that event to happen, so probability will be 1. If there's not chance at all for that event to happen, probability will be 0. So between 0 to 1, you will have the probability of any event to happen. Remember one more point, right? Regarding this, probability of any event to happen plus probability of any event not to happen, that we should denote by E bar above it, that is equal to always 1, right? E bar means not E, not event E to happen, right? This is very, very important. Sometimes it will be very useful in problem solving, right? Probability of any event to happen and probability of any event not at all to happen, their addition will be plus. So sometimes we can calculate probability of any event not to happen at all. I don't want E event to come at all. So that will equal to probability of means that is 1 minus probability of this event to happen. So sometimes this way some calculation will be easy for us. We'll see through problems. Right. So let's see the problems here. So first question I'm putting here: a five, a five-digit number formed by the digits by the digits 1, 2, 3, 4, 5 without repetition. Without repetition is selected at random. At random, find the probability. Find the probability that number is first divisible by 2, second divisible by 3. So a 5-digit number formed by the digits 1, 2, 3, 4, 5 without repetition is selected at random. Find the probability that number is divisible by 2, second divisible by 3. Okay, just try this. I'll just give you 5 minutes. I'll just come, right? Okay. So, so these are the five, 1, 2, 3, 4, 5. These are the 5 digits number we have to form by the digits. These means digits should be 1, 2, 3, 4, 5 only in that 5-digit number. Right? There should not be 6. There should not be 7 like that. And no number has to be repeated. And randomly we are selecting. Find the probability that number is divisible by 2. So see here. Right. 1, 2, 3, 4. Right. So we have 5 digits to be placed. Right. Out of these numbers. But we have to make sure that the number should be divisible by 2. See, you can select a number in any manner. 5-digit number can be prepared by any manner, right? So see, total number of number prepared by this can be anything. You can put 5 here, you can put 4 here, you can put 3 here, 2 here, 1 here at this place, at the unit place. But we have to make sure what is my favorable event. The favorable event will come when you have the numbers, these 5-digit number divisible by 2. And for this, the unit place, the number should be also divisible by 2. Then whole number will be divisible by 2. So here the unit place, your number can be either 2 or 4, right? Either 2 or 4, right? From here you can keep either 2 or 4 at the unit place, and then you keep any number here. You will always see that number will be divisible by 2. So what are the 2 possible ways to fill this unit place? It's 2 ways only. 2 ways. That only 2 ways by which you can select a number and keep it over here. Either you will select 2 or either you will select 4 and keep it over here. No other number is here. Now, once any number is selected, suppose you have selected 4, then how many numbers are left over? Right? So one number is used 4. So 1, 2, 3, 4. 4 numbers are still with you. Right? Suppose you have selected 4. So still how many numbers are left? 1, 2, 3, 4. 4 numbers are left with you. Right? So out of these 4 numbers, you can select any number. So there are 4 ways. There are 4 ways to fill. There are 4 ways to fill this place. Right? The numbers should not be repeated. So 2 numbers are consumed. 2 numbers are consumed. Let's say 1, 4 or 1, 3. Then how many numbers left? 1, 2 and 3, 5. 1 to 5 is left, let's say. So there are 3 ways you can put any number. Right? So 3 numbers are consumed. 2 numbers are left. So there are 2 ways. And finally, there is only one way to fill this place. Right? So in this way, you have to fill it your column. So total number of ways will be what? Right? 1 into 2 into 3 into 4 into 2. Right? 48. 48 ways. 48 ways are there. Right? These are the favorable ways. Right? Favorable ways. Now total number ways is what? To select any 5 number, right? To prepare a 5-digit number, right? So here you can select how many ways? 5 ways only. Right? There is no constraint because we are not looking for any divisible by 2 or divisible by any number. So 5 ways are there. How many left? 4. So 4 ways are totally with you to fill it this place. Then you have 3 numbers left. So 3 ways are there to fill this, right? Then you have 2 ways. Then only 1 way. So total number of ways, how many there? 1 into 2 into 3 into 4 into 5. That is 120 ways. 120 ways are there to create 5-digit number, irrespective whether it's a divisible by 2 or not divisible by 2. Right? So these are the ways, total possible case. You can take as a sample space also. These are a total numbers in a sample space which can make 5-digit number. But out of this, only 48 ways are there which will make the number to be divisible by 2. So in this way, you have to bring the probability definition. The probability will be what? For this event to happen. For this event to happen, favorable ways are 48, right? And out of 120 you have to keep, right? So it will be around 0.4. So 40% chances are there that you can get a number which are divisible by 2. Next is number divisible by 3. Next is number divisible by 3. So see this, when I can say number divisible by 3, when the summation of all the digits in a number is divisible by 3. So if you add this 9, right, 10, 15. So 15 is the summation. 15 is the summation of basically total number. If you add, right, if you add total number of digits 5, 4, 3, 2, 1, right. So you see the summation is totally divisible by 3. When the summation is totally divisible by 3, doesn't matter how you arrange this. Summation will be always of this 5-digit number will be 15 only, and that is divisible by 3. So it's a sure event. This is a sure event to happen. Number will be divisible by 3 only. Whether you keep 5 first, 1 last, 3 here, 2 here, doesn't matter. Summation, if you do of all the digits in a number, you're going to get 15 only. Doesn't matter how you arrange. So number will be divisible by 3 only. So it's a sure event to happen. So probability will be here 1. Right? So probability will be 1 here. Right? So second, you see, we have 1, 2, 3, 4, 5. So 15. Summation is 15. So if any number has to be divisible by 3, the sum of digits should be also divisible by 3. The sum of digit is totally divisible by 3. So this is a sure event, right? Probability of this event to happen is equal to 1. We'll take more problem. If out of 20 consecutive, if out of 20 consecutive natural number, two are selected at random. Two are selected at random. Find the probability that their sum, right, that their sum is an odd number. If out of 20 consecutive natural number, from 1 to 20, two are selected at random, find the probability their sum is an odd number. So when you can have this, see, slide what you are saying, we have 1, 2, 3 goes to 20 consecutive natural number. I am going to select two number randomly. Maybe 3 I can select, 1 I can select, 4 I can select, 19 I can select. Any two number randomly I am going to select from 1 to 20. I have to make sure that their sum is an odd number, right? So when the sum can be an odd number, right? What, or when is my favorable number of cases will come? So number of favorable cases, right? For that we are looking. So we should know this point, that if an odd number is there and it is added to another odd number, that brings even number, right? Or if there's an even number added to even number, that is also brings even number. And if there's an odd number, right, and the one number is even, if you add it, you will get odd. odd number, right? So we have to see this, that this case comes, one number should be odd and one number should be even, then 100% their summation will be odd only. So we have to see how many odd numbers are there and how many even numbers are there from 1 to 20, right? So we have 1, 3, 5, 7, 9 goes to 19. So these are basically, you will see that you have 10 odd numbers. 10 odd numbers. If 10 odd numbers are there, left is also 10 numbers, those will be even. So it will be 2, 4, 6, 8, 20. So these are 10 even numbers. 10 odd numbers and 10 even numbers we can have. Now we have to find the probability of the favorable event. Right. So probability of this event to happen, which has been discussed, the summation of two numbers has to be odd. So one number I have to take from here and one number I have to take from here, right? I don't have to take both the number from here or both the number from here, right? One from odd and one from even. If I take a number, I will get summation of two number odd. So from 10 number I have to select one number. So 10 C1, and my task is not done. I have to again pick one number, but from this set. So again, out of 10 even number, you have to select one. 10 C1 into 10 C1. So these are the favorable numbers, right? Or event. But in total, what is the sample space? In total, how many ways you can select two numbers? From 20, you can select two numbers. Because 20 digits are there. Out of 20, you have to select two number, right? That is the total sample space it can be. Means what are the ways to select two numbers from 20 number? That is 20 C2. That is the total sample space. But this will not be favorable. Favorable will come when I select one from here and one from here. Now, you have to just solve for this. But 20 C2. 20 C2 is what? Factorial 20, right? Here factorial 2 divided by factorial 18, right? Factorial 20 I can write 20 into 19 into factorial 18. Factorial 2 is 2 only, and this is factorial 18. So this factorial 18 and this factorial 18 will cancel off. So 10, 190, right? 190 will come. And 10 C1 is also 10, and 10 C1 is also 10. This is 190, right? So it is basically 10 by 19. So 10 by 19 is the case. Right? Take one more question. An integer is selected. An integer is selected at random and squared. Right? Find the probability that the last digit of the square is 1 or 5. So here we have to find that an integer will be selected at random and it will be squared. I have to just focus on the last digit. What is the probability that the last digit will be of the squared number is 1 or 5? See, we don't know how many. See, there are so many numbers, infinite numbers are there, right? So what will be the sample space? The thing is, we have to focus on the last digit number only, the last digit of the squared number, right? So whatever number you select on real number line, the last number only we have to focus. So last number can be 0, 1, 2, 3, right? 4, 5, 6, 7, right? And then we have 8 and 9, right? For example, this is 10, 100, 1000, this is 111, 121, 141, 211. The last digit is more important to us. Like this is 89, 999, right? Because we have to find the square of the number and then we have to focus on the last digit. So last digit square number, if you have to focus, so number which you are taking, here also the last digit will be only important for us. The last digit of any number is only important for us, because if any number you square up, the last digit squared only will be coming with us, right? For example, if I square, this is just a number, this is any number from here. So this is just a number, whichever number you select, the last digit is this. This is squared of that number squared. So whichever number is there, if you square it, the last digit will be also 0 of a squared number, right? If you take any number whose last digit is 1, if you square it, then also you will get 1 only, right? Here, if any number is there whose last digit is 2, if you squared it, so this 2 will be also squared, right? So if example 22 is there, right, you have to make it 22, so it will be 4. Now whatever comes over here, I don't have to bother, right? So we have to just find the square of s. So last digit will be squared up to 4. Here last digit will be squared to 9. This will be 4, right? 16 will be there. So we have to take the last digit as 6. This will be 25. So last digit will be 5. 6 will become 36. Last digit is 6. 7 square become 49. So last digit will become 9. This is 64. So this will become 4. And 9 square is 81. So 1 will be left over at the last digit. Only the unit place we are most bothered about. Unit place. Now question is saying the squared number's last digit is either 1 or 5. So either 1, right? Either 1 or 5. 5 is anywhere this. So how many events, possible cases are there? 10, right? Possible cases are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So out of 10, how many are favorable? Right? Out of 10, how many are favorable? Only 3. So this will be the probability, 3 by 10. Okay. Another question. A committee of 4 person, a committee of 4 person is to be formed from 4 girls, and 5 boys, from 4 girls and 5 boys. What is the probability, that committee what is the probability that a committee will have number of boys less than number of girls, less than number of girls. So let us put in this way. Let's take number of boys at one column, right? Number of girls here, and out of them only I have to make a committee, right? So this is committee, right? Number of ways of selection for committee. So we have 4 girls and 5 boys. Total how much girls and boys are there? 4 girls and 5 boys. So they are saying you have to see, you have 9 people, 9% you have in total. 5 plus 4, 9. And out of them you have to make a committee or group, you can say, that consists of 4% only 4%. But in that 4%, number of boys should be always and always less than number of girls, not equal also, less. So what are the possible ways? See, what are the total cases can be? I have to select how many? 4 people from 9. So total case will be what? Total case will be what? Right? Out of 9 people, you have to select 4 people. That is 9C4. 9C4. If you want to solve this, it will be factorial 9 divided by factorial 4 and factorial 5. Right? 120. These are the total ways. Total way to select 4 people from 9 people. Doesn't matter boys are more or less, girls are less, more, doesn't matter. Total ways are we are coming up with that. 126 will be there, I think. 126. Now, we have to find some favorable cases. Favorable cases means this case. Number of boys should be less than number of girls. So what are the possible case? Number of boys has to be less. So it means boys can be totally 0. If boys are total 0, so whole committee will be consist of girls only. So 4 girls. Right? 4 girls. So committee of 4 people we have to create. Right? This is favorable. Let's say I increase number of boys 1. So how many girls will have? 3. This is also favorable. Right? 1 boy and 3 girls. It is favorable. So for first cases, what is the way to select? It means 0 boys you have to select. Right? Or you can say from the 5 boys, 0 selection. And from the 4 girls, you have to select 4. 4C4. That is equal to 1 only. Right? That is this case. Right? And this case will be what? You have to select 1 boy out of 5. So it is 5C1. And thing is not done yet. So you have to select 3 girls also out of 4. So 4C3. 4C3. If you select, it will become 20. 20. Any other ways? Suppose I keep 2 boys. If I keep 2 boys, what is left over? Only 2% is left over in committee. So this is not favorable. This is not favorable for me. 2 boys, 2 girls cannot come because boys has to be always less than girls. Here the boys is equal to girls. So after that, what you will do? You don't have any of the favorable cases. Only 2 favorable cases are there out of this total. So favorable cases are what? 20 and 20. 20 plus 1. 21. So favorable cases basically 21 out of total cases 126. Right? Then more problems we'll see through another topic, conditional probability. Conditional probability. and this is the base for total probability and Bayes theorem, right? So what this conditional probability is there? Suppose I'm throwing a dice. Throwing a dice. So what are the possible sample space? I can get 1, 2, 3, 4, 5, 6, right? Conditional probability. It's a base for, right, for total probability questions, or you can say Bayes theorem, which is very important for the problem. So a condition, what is there? Condition means there is a certain constraint is there, and then you're calculating probability after that. So let's say there's a throwing of dice. I want to find a probability of 2. I want to find out what is the probability 2. So it will be 1 by 6, right? 2 can appear one time, right? It's 1 by 6. Now the constraint, the condition is what? Suppose you are creating an event out of this that is even, right? Suppose you are creating a sample space of even numbers. That is 1, this is 2, right? And this is 4 and 6. You're creating a sample space or out of this only, right? Or you have created a new event. This is also event because subset is there, a new event is there, right? Now out of this, now you want to calculate what is probability of getting 2, right? So what is the probability of getting 2? You have to select when even numbers has been selected separately. So probability of getting 2 when even numbers is selected separately. When even numbers are selected, out of that even numbers, what is the probability of getting 2? So you can see that is the answer will be 1 by 3. So probability gets changed if you put a new condition in between. So what is the probability of 2 when even number has come up total? So if even number has come up total, it can come up with 2, 4, 6. Out of that, probability of 2 will be 1 by 3. Right? So this is the condition. The condition will be always at here. After this has happened, this event has happened, what is the chance of getting this event? 2 to heaven. Right? So here we bring the conditional probability definition. Probability of getting A event when B has already occurred. It means that probability event A, right, given that event B has occurred. Not tell me what is the probability of event A. If event A is dependent on event B, definitely event A will be changed. Right? If event A does not depend on event B, so event A probability will not change. We will see later also independent events. So probability of A when event B has happened, right? So probability of event A given that event B has occurred, right? If we see from Venn diagram, more clarity will come. Suppose this is my total sample space. This is my total sample space, and there are two events here. That is event A and event B. Right, this is B, this is A, right? Now I want to calculate this probability of event A when B has occurred. So you are looking for A from B. So B is your new sample space, right? As you can see here, probability of 2 you are getting from this sample space. But when you say the event even has occurred, event of even number has occurred, then what is the probability of 2? Your sample space changed to this. You're looking from this only to get probability of 2. So here also when you're saying probability of getting A when B has occurred, so your new sample space is event B. Okay, this is new sample space. Yes. So this become a sample space when you say this. So here B becomes sample space. Right, out of B you are looking what is A has occurred. So B has occurred and B is coming out of sample space only, right? So B has occurred. From the B, how much A is happening? This much only, right? A intersection B only. If B becomes a new sample space, see B has occurred, even B has occurred, so even B become the sample space to check out what is the favorable event of A. So B become a sample space. Out of B, I can see only this A part is common. So this green portion is coming favorable, or the green portion is nothing the probability of A when B has occurred. So how I can express this? It means that I am looking for probability of A intersection B, right? When probability of B has occurred. When probability of B has occurred. So this is my conditional probability understanding. Probability of A when B has occurred is probability of A intersection B divided by total probability of B. So out of B, this much is only is my favorable part, because in this part event A is occurring. Similarly, you can write this way also. For example, I want to write probability of event B when A has occurred, right? What is the probability of event B when A has occurred? So A is a new sample space. So A becomes a new sample space for this, right? For this, B become a sample space, and for this, A become a sample space. Right? A become sample space. A become a sample space, right? Right. You're looking for B from A. You're looking for A from B. So automatically your sample space will be switched. So from here, for this, I want to know when A has occurred. Out of this, how much B is occurring? I will say again the green portion only. The green portion is only something which is common, right? So this will be also, numerator will be also again same, right? When A has total occurred, when A has total occurred, what is B? So A has occurred. This is the event A. After that, how much is event B? Only this common portion. So this is the only thing we are getting. Divided by sample space is probability of A. So out of A event, this is your common portion. This is the common portion which is there. So this is probability of B when A has occurred. Now from both the equation, you see numerator is same. Numerator is same. Numerator is same. From here you see the numerator is this, numerator is this. So numerator is nothing but probability of B multiplied with this thing. Numerator is probability of this multiplied with this thing. So if I want to calculate the common portion A intersection B, so probability of A intersection B, right, that is equal to probability of B multiplied with probability of A when B has occurred, right? Or I can write from this I can cross multiply this probability of A multiply with probability of B when A has occurred. Both ways you can express your this. Now with this continuation we have the discussion about independent events. What are independent events? Independent events. What are independent events? So very easy to see. Independent events, they're independent to each other. That's it. It means two events A and B are called independent events, if probability of occurrence or non-occurrence of A will not affect the probability of occurrence and non-occurrence of event B. Right? That's a independent. Two events A and B are called independent events if the chances of occurrence and non-occurrence of A has nothing to do with the chances of occurrence of non-occurrence of B. That's why we say totally independent to each other. Right? For example, right, suppose an event happens and in that event head-on coin has to be expected. Right? So it has nothing to do what is the probability of getting tail. Right? Because probability of getting head is fixed 1/2. Right? Similarly, probability of suppose another event B is there and it is getting 2 on dice. So its probability of getting 2 on dice will be 1/6. It has nothing to do with the probability of 4, probability of 5. So probability of 2 is fixed. Right? Irrespective what is the probability of other. So if A and B are independents, right? If A and B are independent, then independent events, then right, then we have this thing, right? First we have studied this conditional event, we have seen conditional probability. So probability of A when B has happened, probability of A when B has happened. So whether B happens or not happens, probability of A will not be suffered. It will be probability of A only. That's what we were saying. Probability of event A when B has occurred is equal to probability of A only, because A and B are independent events. A and B are not dependent to each other. Similarly, probability of getting B event when A has occurred is equal to the probability of B only. It has nothing to do with whether A event has occurred or not. So what is the B probability? It will be static, right? It won't be changed whether A is occurring or not occurring. Right? So in this way, independent happens. Do some remodification in my condition probability. Right? See this? So just now we have written this point, probability, right, of A, probability of A intersection B, that is equal to probability of B, right? Right. Okay, so probability of A when B has happened. This we have studied right now, right? Here in conditional probability. Probability of B multiply probability of A when B has happened. And also we have seen this also. this also, this two thing, it is also equal to probability of A multiplied with probability of B when A has happened. So this was the expression for P probability of A intersection B. Right. And this is also equal to probability of A multiplied with probability of B when A has occurred. This was the formula. Now we are saying this thing and this thing. In this thing, some changes need to be done because A and B are independent events. So whether B happens or not, probability of A will not change. B and A are independent events. Whether A happens or not, B probability will not change. So that's what we are seeing over here. That's what we are seeing over here. So for independent events, what will come? For independent events, this will be probability of A only, and this will be probability of B only. Right, from here. Right. So now probability of A intersection B comes out to be probability of A multiplied with probability of B. Like this. Right. If there are three events, suppose there are three events happening and all the three events are independent. So you just multiply with the probability of A, probability of B, probability of C. Question will give you individual probability, question will give you. We'll see through question. You have to just simply multiply the individual probability and you will get the probability of A, B, C, all three things to happen. So in general, what we can say? In general, if A1, A2, right, A3, let's say AN are independent events, are independent events, right? Then what we can say by the simple understanding, then probability of A in A1 intersection A2 intersection A3 goes to intersection AN events, that is equal to probability of A1 events multiply with the probability of A2 events multiply with the probability of A3 events, keep on going, multiply probability of nth event. We have to just keep on multiplying. Now we see the question. Now, question, in a class 40% of students right read math, right, 25% right read physics, so in a class 40% of students read maths, 25% physics, and 15% both math and physics. Find the probability that the student reads first maths, given that he reads physics as well, also. It's a concept condition probability is coming, right? Then physics given that he reads maths. So in a class, 40% is there. Students, 40% of students read maths, then for 25% of physics, 50% read both. Find the probability the student reads maths given that he reads physics as well, and then second physics given that he reads maths also. So this is some conditional probability is there. So see, when we are giving this percentage, so already we can assume any, let's say 100 students are there. Out of that, 40 students reads like this, 25% read like this, right? So here, in terms of probability, also we can take this, right? So probability of people, persons, or students reading maths is directly given as 0.4, right? And probability of a students reading physics, let's say 25%, so it's 0.25. And probability of person studying physics as well as maths is given as 15%, 0.15. So I have to find, first, try to write in a symbolic form. I have to calculate what is the probability of the students studying maths given they study physics also, right? So that is what probability of people studying maths intersection physics divided by probability of people studying physics. This we have to just put the condition probability formula. So this is given to us 0.15 and physics is given 0.25, right? Around 0.6. Second, we have to calculate probability of people studying physics given they study maths as well. So same will be there in numerator, maths intersection physics by conditional probability, but you have to denominator will be probability of maths. So this is 0.15, this is 0.40, that is equal to something 0.375. So just formula we have to apply. Next question you see, the probability of hitting a target by 3 persons are half, 1 by 3 and 1 by 4 and 1 by 4. Right? Comma, when they fire simultaneously, right? Find the probability that find the probability that, so some cases are there. First, all three will hit the target. All three will hit the target. Right. Second is no one will hit the target. No one will hit the target. Right. Third case is at least one. Right. At least one will hit the target. And the fourth is Exactly one. Exactly one will hit target. This is very important, interesting questions. Every case is different from each other. Right. It's so we have a probability of hitting a target by 3% are this 1 by 2, 1 by 3, 1 by 4. When they fire simultaneously, find the probability of each of this case. So see, with 3% are there, let's say 3% are ABC. Right? 3% are ABC. So probability of hitting a target by first person, let's say it is equal to half. Probability of hitting the target by the B person or second person is 1 by 3. And probability of hitting the target by C person or third person is 1 by 4. Also hitting the targets by each of them are independent events. Right? What skill set this person has had, this is different from the skill set of B person. Different skill set C person will have. Right? So basically, this person hits the target, that probability is nothing to do with the probability of B person hitting the target. Right? Similarly, the probability of hitting the target by C person has nothing to do with the probability of B person hitting the target. So these are independent events. These are independent events. For example, in Olympic also, if there are shooters, so we shooters, whatever this one person shoot has the probability to hit the target has nothing to do with the probability of hitting the target by the other person. Right? So that is also you can take in this way. Right? If archery is there, if you have to hit the target, so one Olympic person, right? In Olympic, one person is hitting the target has nothing to do that other person will hit the target or not, or in what probability it will hit. So because all persons will have different skill set, so their skill sets are totally different or independent to each other. So they will hit the target or not hit the target, that is totally dependent on their own skill set, not dependent on other skill set. So these are independent events always. So these are independent events, right? So in this ways, if I try to calculate first point, all three will hit the target, right? All three will hit the target. It means what? We have to find probability of A intersection B intersection C. Means all three is coming. A and B and C, right? All together hit the target, right? So it is nothing but probability of A multiply with probability of B multiply with probability of C, because they're independent events. So 1 by 2, 1 by 3 and 1 by 4. So 1 by 24. This is the probability. These are the chances when all the three will definitely hit the target. Second is nobody will hit the target. Nobody will hit the target. No one will hit the target. So it is in negation. It is in negation basically. Right? So basically you see probability of A also not hitting the target, also B not hitting the target, also not C hitting the target. All three should happen together. Right? Intersection means and, right? Intersection means and, right? So all this person all together should not hit the target. A should also not hit the target and B also and C also, right? So this means what? I have to just calculate the probability of these people not hitting the target, right? So you remember this point we have seen. These are independent events. So this will equal to probability of A not hitting the target multiply with probability of B not hitting the target and probability of C not hitting the target. Right? Independent event, just you have to multiply. So probability of A hitting the target is half, not hitting the target will be 1 minus half, right? So we have seen this part, right? Half. Probability of B hitting the target is 1 by 3, not hitting the target is 1 minus 1 by 3, right? So it is basically 2 by 3. Probability of C hitting the target is 1 by 4, not hitting the target is 1 minus 1 by 4. So basically it is 3 by 4, right? So it is 1 by 4. Now the third case is interesting. When we have at least one will hit the target. At least one means what? Minimum one. Minimum one will has to hit the target. It can be 2, it can be 3 also. Doesn't matter. So minimum one has to hit the target. So what are the possible cases? So we have to find at least one hit the target. Hit the target. Right? At least means what? Minimum one, because three people are there. Right? So minimum one has to hit a target. Means target has to be hit by any one of them, or two of them, or three of them. So what? See, let's try to understand here. So minimum means hit a target. It means I can have this case also, that all can hit the target. Minimum one, right? So here all the three hitting the target will come into this category, right? Or what can be the category? Minimum one will hit the target, right? Suppose A hit the target, but B does not hit the target and C does not hit the target. This case can also come. Minimum one has to take the target. So A is taking the target, B negation is there, C negation is there. So B and C is not hitting the target, but A is hitting the target. So this is also one of the case which is possible under case 3. Right? Suppose now A is not hitting the target, but B is hitting the target and C is not hitting the target. This is also favorable case. Minimum one has to hit the target. Same for we can do for C also. Right? A not hitting the target, right? B not hitting the target, but C hitting the target. This is also minimum one is hitting the target. Right? Or what cases can be there? Two can hit the target. Any two can hit the target, third will not hit the target. Right? So A is hitting the target, B is hitting the target, but C is not hitting the target. So minimum one, two is hitting the target. That also the favorable case. Or right, A is hitting the target, right? B is not hitting the target, and C is hitting the target. This can also come. A and C is hitting the target. Next, the last case can come. Probability that A is not hitting the target, B is hitting the target, C is hitting the target. These cases will come. 7 cases will come for this thing. If you want to get at least minimum one, you can see minimum one will take here in terms of 3. All 3 hitting the target. Here, one A is hitting the target. Minimum one, minimum one, minimum one. Minimum one can take 2 also. Can take 2 also. Can take 2 also for hitting the target. So this will be very lengthy. What you have to do? Just you have to. These are independent events. So you have to just multiply probability of A, B, and C. Probability of A multiply with probability of B negation, C negation, plus probability of A negation multiply with B multiply with C negation. So this thing you have to do a lot of times. It is very calculative. But this thing, such type of question will not proceed like this. We have to find this. At least one, right? At least one. Probability of at least one hit target. At least one hit target. It means if I can say probability of at least one hitting the target, it means I can say 1 minus probability of no one hits the target. Right? All three miss the target. All three miss the target. All three miss the target. Right? We'll just find all probability of all 3 miss the target and we'll subtract with 1. So 1 minus probability of all 3 miss the target definitely will be coming in these 7 cases only. Right? In these 7 cases only. So basically we have to find this. 1 minus probability of A is not hitting, B is also not hitting, C is also not hitting. Right? And you subtract this case. If you take out this case from your sample space, you're going to have this only in your sample space. Right? Means outcome. Right? If you take out this case out of your total possible cases, you're going to get at least one will definitely hit the target, because you are subtracting that probability in which no one hits the target. And if you take out no one hits the target, definitely you're going to be left over with at least one hit the target, or 2 can hit the target, and all 3 can hit the target. And we have just calculated here probability of nobody hits the target. That is 1 by 4. 1 by 4. We have to subtract 1 minus 1 by 4. So that has become 3 by 4. Right. So probability 1 minus 1 by 4. That is equal to 3 by 4. very easily. This is the method. This is the way you have to proceed in such type of questions. I just told you trivial method, conventional method, but question is not expecting you to calculate by this. Question wants to use this logic only, right? So get this logic right. The last case you see, the last case is exactly one will hit the target. Now this is very specific. Exactly one will hit the target, not two, not three. So we are bringing lot of constraint here. So fourth is exactly one hit the target. So exactly one hit the target means what? At a time, one only should hit. So there can be one case when A hit, but B and C should not hit. Then only I can say exactly one is hitting. But you can expect B is hitting, other not hitting. So A is not hitting, but B is hitting, C is not hitting. You can expect C to hit, A B will not hit. Like this. So three cases will only come. Three cases will only come. Now you have to just put up the things. They are independent events. So probability of A multiply with probability of B negation multiply with probability of C negation plus probability of A negation, right, multiply with the probability of B, probability of C negation. Here we have to see here, right, probability of A negation multiply with probability of B negation multiply with probability of C, and every value is known to you. Every value is known to you, right? So probability of A, that was half, right, and this was 2 by 3, and this was basically 3 by 4, plus this is half, this is 1 by 3, this is 3 by 4 was there, this was half, this was basically 2 by 3, this is by 1 by 4 was there. Right, if you solve this, I think you will get, just you can cross check also, it will be 11 by 24. Okay. Now we see one more question. Two players A and B, right, alternately keep rolling, right, a fair dice, the first person to get 6 wins, 6 wins the game. Now if A starts, the probability of his winning is, very standard, very popular question. Okay, so see, they're saying two players are there only, A and B, alternately keep rolling a fair dice. Okay, the first person to get 6 wins the game. That's how we'll stop the game. If A gets the 6, he wins the game. If B gets the 6, he wins the game. If A starts first, right, what is the probability of his winning? Right, see, probability of win is what? Probability of anyone to win is to get 6, and that's probability is what? 1 by 6. Right, probability of loss, right, that is equal to 1 minus 1 by 6, that is 5 by 6. Probability of win means what? That is equal to probability of getting 6 only, right, and probability of loss means what? Probability of not getting 6, that is only 5 by 6. Same thing. Win means getting 6, not winning means we are not winning, means that is a loss for us, that is 5 by 6. Now probability of A to win when he starts, so probability of A to win means what? If he starts, it can happen in his first attempt. In his first attempt he gets 6, he wins, right, he gets 6, he wins. Or let's take like this, right, A wins, right, so that he will win, right. Suppose A does not win in his very first attempt, so B will throw the dice, right, so B should not win, I want A to win only, so that next attempt should come with A back again, then A can win, like this. If a first attempt A does not get 6, then I would expect B should not also get 6, so that again A should get the opportunity to get 6. So this should be the case for A to win. We are looking for A to win, right? Then what can happen? In very first attempt A does not win, so B should not also win. Then suppose in the third attempt A also fails again, does not get 6, A does not win, then it will go to B. B should not win, so that again the dice come back to A and A wins. Oh my god, this will go no time, we don't know when will end, right? But I know this will be, we have to add such type of cases up to infinite times. We don't know when we have to stop. Suppose this time, next time A does not win over here, A does not get 6 over here, then B will go, B should not also win, then again we'll get the opportunity to get 6. So this will keep on running. So probability of getting A means probability of getting 6. So this is 1 by 6. These are independent events. So so here will be 5 by 6, 5 by 6, right, 5 by 6 whole square, and this is 1 by 6. This will be what? 4 times 5 by 6 should be getting. 1 minute. By 6 square. And this is 4 times you'll get 5 by 6. And 1 time 1 by 6. This will run to infinite. Right? Probability of winning is 1 by 6 for anyone, and probability of not winning is 5 by 6 for anyone. And all the independent events are there. You can just multiply their probability. So here we have to add up something. So if you see, this is the progression, this is the geometric progression where the first term is 1 by 6, where the first term is 1 by 6, and common ratio you see it is 5 by 6, right, whole square, right? Common ratio is 5 by 6 whole square. So summation of a GP up to infinite is first term divided by 1 minus common ratio, where this is less than 1, right? You have to just this keep the value. A value I will keep 1 by 6, right? R value will keep 5 minus 6, 5 by 6 whole square, right? This you have to solve, and I think you will get 6 by 11. Now we'll see the total probability, another very beautiful concept for the Bayes theorem. Total probability. Total probability. First we studied conditional probability, then we are studying total probability. Now we are studying these two things for Bayes theorem only. Right? Actually, the Bayes theorem is only for that only. These two things are very important. Bayes theorem questions are asked very much, right? But there's advanced topics in probability. Right? So what is total probability? It's very easy to understand if we try to understand with some geometrical picture. So let A1, A2 up to AN be n partition of a sample space and let A be an event which can occur either with A1 or A2 or AN. Right? What we have written, let A1, A2, A up to AN, right, be n partition of a sample space, means events only, right? Partition means what? It's a subset of sample space. So A1, A2 up to AN are n sample events of a sample space, and let A be an event which can occur either with A2, A1, A2 or any one of the nth partition. Then means what? For example, we are saying this, right? So but this is my total sample space. Total sample space I have divided into n parts. Let's say this is, right, A1. Let's say this is A2, right? Let's say this is A3, right? And let's say this nth partition is there, right? So this A1, A2, up to AN are the n partition of a sample space, and let A be an event which can occur either of the this. So let's say this is an event. This is an event which can occur either of the this partition. You can see also some portion is coming in A1, right? Let's say this is a event. This is a event A. This is a event A, which is occurring in all the three partition. Through problems we will get more understanding, right? So this is A event is shared by the A1 also, right? A event is shared by the A3 also, this much portion, right? A event is shared by the A2 event also, this one, right? And A event also shared by the this one part, right? This much also, right? Then I want to know what is the total probability of A, because A is coming from all the events, all the partition. What is the total probability of this A event to happen? Because A event can happen with A1 also, A event can happen with A2 also, A3 also, A4 also, A5 also, nth event, right? So I want to know the total probability of this to happen. Now total probability of A event to happen, that will also depend on what is the probability of A1 to happen first, right? What is the probability of A1 to happen first? That will only affect the probability of A to happen from A1, right? So individual events probability also I should know. Then only I will enter inside and find it out what is the probability of A from A1. So let's see here. Very easy to write. So total probability of A I want to write. Total probability of A I want to write. Means what I can say? I want probability of A intersection A1. A intersection A1. Right? I want this. Plus I want probability of A intersection A2. Right? Plus I want probability of A intersection A3. Right? Like this, I want probability of A intersection AN. Right? Because this shaded portion in each of the A1, A2, A3, I want to collect. That is the total probability of A. So A can appear from A1 also, A can appear from A2 also, A3 also, and nth also. Right? So in this way, you have to find this. Now we know this from a conditional probability. From a conditional probability, I know this how to break this. So probability of A intersection A1 means what? First, I should know what is the probability of A1. What is the probability of A1? What is the probability of A1 first? Because A1 is occurring from this sample space only. So I should know what is the probability of A1 out of this sample space. So this is the probability of A1. Once I have entered into this, then what is the probability of A getting from A1? So conditional probability is there. So once the probability of A1 is coming into the picture, what is the probability of A? Right? Then A2, right? What is the probability of getting A2? Once A2 event has happened, then what is the probability of getting A from A2 event? Like this. Plus the probability of A3 event has happened. So once the A3 event has happened, what is the probability of getting A? Similarly, let's say nth event has happened, and when this nth event has happened, what is the probability of getting A? So like this, if we add all such things, we'll get the total probability of A to come in picture. Example. There are 3 bags A, B, C. Bag A. Bag A contains bag A contains three red and four green balls. Right? Right. Bag B contains bag B contains bag B contains two red and five green balls. Right. Right. There are 3 bags A, B, C. Bag A contains 4 red and green balls. Bag B contains 4 red and 3 green balls. Right? Bag B contains 4 red, right, and 3 green balls. 3 green balls. Right? 1 minute. I'll just change this only. This is fine. A containing, this is for bag B, bag A. Bag A contains 3 red and 4 green balls. Bag B contains 4 red. Here you have to change 4 red. Bag B contains 4 red and 3 green balls. And bag C contains, right? Right, bag C contains 2 red and 5 green balls. 2 red and 5 green balls. Now, right, A bag is selected. Right? Right. A bag is selected. A bag is selected. See, this is just English. A bag is selected at random. A bag is selected at random. And ball is drawn. And ball is drawn from it. Find the probability. The selected ball is red. The selected ball is red. The selected ball is red. There are 3 bags A, B, C. Bag A contains 3 red and 4 green balls. Bag B contains 4 red, 3 green balls. Bag C contains 2 red and 5 balls. Right? 5 green balls. Now a bag is selected. Now this is not a bag. This is a bag. Simply a bag. Right? A one bag. Right? So you can this is just talking about one bag is selected. Not a bag is selected, just a one bag. Right? One bag is selected at random. That's why it is saying at random you are selecting any one of the bag. So A does not mean a bag. It's just saying one bag. So one bag is selected at random and the ball is drawn from it. Find the probability that the ball will be red. So see, this is the total probability of red ball I have to calculate. If you see here, this is a bag A, right? Bag A. This is bag B, right? And this is bag C. Bag C. Right? This is bag C. Now here you see bag A contains 3 red and 4 green. Right? 4 green. Bag B contains 4 red, 3 green. Right? And bag C contains 2 red and 5 green. Now a bag is selected at random. What is the probability of getting red? Now see, red is appearing in this also. Red is appearing this also. Red is appearing this also. right? So if you try to see from this perspective, like this, we have three things over here: bag A, bag B, bag C. And there's an event created, that event discuss of the red ball to happen, right? So red can appear in bag A, bag B, bag C. I have to calculate what is the total probability of getting red ball, right? Red ball. It's just similar to what we have discussed in the theory. So basically, red can appear from here also, A also. Red can appear from here also, B also, and red can appear from C also. From C also. So pink, green, this blue, all three this shaded portion value I should know. That will be total probability of red ball. So how to write total probability of red ball? We can write like this. See, first we have to find what is the probability of getting A. Then I can find in A what is the probability of red, right? Then we'll see what is the probability of getting B. Then in that I can find what is the probability of red. Then we'll see what is the probability of C. In that I will go and check what is the probability of red. So if we have to check red portion, I have to come from outside to inside, because red ball is shared in all the three bags, right? All the three bags, so we have to check in each individual bags, right? What is the probability of getting red? So in that we have to go from the bag to inside to check the ball is red or not, right? So first we have to get this probability. What is the probability of getting A bag? So once the A bag is selected, what is the probability of getting red? Plus, what is the probability of getting B bag? Once the B bag has been selected, what is the probability of getting red? Plus, what is the probability of getting C bag? Right. Once the C bag is selected, what is the probability of getting red? Like this, we have to create a conditional probability, right? Right. Because first you have to select a bag. What is the probability of that bag to select? And once that bag is selected, what is the probability of checking or getting red ball? So there are three bags. Out of three, you're selecting one. So 1 by 3 is the probability to select A bag. Now once you know this, you're inside the A bag. Inside the A bag, what is the probability of getting red ball? Right? Right, red ball. 3 by 7. 3 by 7. 3 by 7. Out of 7 ball, 3 are red. Plus, what is the probability of getting B bag? 3 bags are there. You're selecting 1. 1 by 3. Multiply with this. In B bag, what is the probability of getting red ball? 4 by 7. C bag probability is 1 by 3. What is the probability of getting red bag from the C ball? So what is the probability of getting red ball from the C bag? So C bag we have selected, probability is that 1 by 3. Right? And what is red ball? 2 by 7. 2 by 7. Just simple as it. Right? So if you select it, it will be around 3 by 7. Okay, I just put one homework question. Tomorrow we'll see to this. Just note down this question. In a bolt factory, 25%, 35%, and 40%, and 40% of the total output are produced by machines A, B, and C. Right? In a bolt factory, 25%, 35%, 40% of the total output are produced by the individual machines A, B, C, respectively. Right? Respectively. Right? Then, and 5%, 4%, and 2% of their respective output, of their respective output, right, of their respective output are defective, are defective, are defective, right? If if a bolt, if a bolt is selected at random, if a bolt is selected at random, if a bolt is selected at random, find the probability, find the probability that it is defective, that it is defective, right? So in a bolt factory, 25%, 35%, 40% of their total output are produced by machines ABC respectively, and 5%, 4%, 2% of the respective output are defective. If a bolt is selected at random, find the probability that it is defective, right? Just note on this, but tomorrow we'll solve this, and after that we'll take Bayes theorem and all. Okay, so we had to find the probability, right, total probability that the bolt is defective. Okay, so we'll keep it up here. Thank you everyone.